Hello everybody and welcome to another umehluko video on grade 12 physical sciences revision. Today we will take the topic of conservation of energy. Now the whole section is on work, energy and power, and we've discussed the idea of work, we've discussed the idea of conservative and non-conservative forces, and now we'll put that together with the idea of the conservation of energy. Now, if you look very closely, we'll see that conservation of mechanical energy is a specific principle in physical sciences, and it states that the total mechanical energy, which is the sum of the gravitational potential energy and the kinetic energy in an isolated system, remains constant. So we've used this principle in some discussions before, but we are defining it here as this, which is important to know because it must be in an isolated system. And what an isolated system means is where the net force acting on the system is going to be zero. That is an isolated system. And the mechanical energy is just the sum of the kinetic energy and the potential energy. Right. Now, in a previous lesson, we saw that the net force is equal to the sum of all the conservative forces and all the non-conservative forces. So conservative forces such as gravitational force, non-conservative forces such as friction and applied force. When we add all of these up, then we find the net force that acts on an object. We can then take this and we can calculate the work done by these forces, and we can see that the net work is then equal to the work done by the conservative forces plus the work done by the non-conservative forces. And in a previous lesson, we saw that this is the statement of the work energy theorem. What we can then do is to find the network, and the network can be given as the change in kinetic energy. That is what the work energy theorem states. So we can say that the change in kinetic energy here is then equal to the conservative force work plus the non-conservative force work. And we can show that the work done by conservative forces is equal to the negative change in the potential energy. And then by rearranging this, we can come to the final statement to say that the work done by non-conservative forces is going to be equal to the work done, is equal to the change in kinetic energy plus the change in potential energy of an object. Okay, so this whole flow is very important because it relies on information that you've learned in previous videos. And so if you don't understand this, go back and watch those videos to catch up again. I find it's always easier to understand something like this when we are dealing with a worked example. And let's therefore go to such an example. So this is the worked example we will deal with now. What we have here is that there is a football player. The football player slides to a stop on level ground. Sliding to a stop, we already assume that there is a force that is acting against the direction of motion. We know that this is going to be a non-conservative force. Using energy considerations, calculate the distance the 65 kilogram football player slides, given that his initial speed is 6 meters per second and the force of friction against him is a constant 450 newtons. So to be able to understand this, let's draw a picture. So here we've got the level ground. You've got the football player is sliding in this direction. Let's say to the right is positive because a force is a vector we can assume that there is a sense to the force, in other words, a positive or a negative, depending on the direction. But let's assume in this case, the movement to the right is positive, and then movement to the left is going to be negative. Okay? We can draw a free body diagram of the forces acting on the footballer. And the force that we have is the force of friction, that is to the left in this case. The normal force, which is the force that the ground exerts on the football player, and also the weight of the football player, the force the football player exerts on the ground. Now what's important here is that these two forces here are in the vertical direction. In the vertical direction, they are not in the direction of motion, and therefore they do not contribute to the work done on the footballer. Okay, so first of all, let's find out what is the work done by the force of friction. Force of friction is a non-conservative force. We can write WNC, which is the work of non-conservative force. And we know that the work is the force multiplied by the distance multiplied by the cos of the angle between the force and the distance. If we have this information here, we can say that we want to find the distance. That's the unknown in this example. So we don't know what that distance is, right? We do know that the force of friction, this force here, is the non-conservative force, the force of friction, which is 450 newtons. And we also know that theta, because the direction of motion and the direction of the frictional force are opposite, theta is 180 degrees. Substituting this in here, we can see that the work done by the non-conservative forces will be 450 delta x times minus 1, because cos of 180 is minus 1. So this is equal to minus 450 delta x. We leave that there because we don't know what x is, but we will use this later on in our calculation to find the work done on the footballer. Now we've also seen that the work done by the non-conservative forces, right, will be equal to the change in the kinetic energy plus the change in the potential energy acting on the footballer. Right, in this case, because the footballer is running on level ground, the height is 0 and the height remains 0. So in this case, the change in the potential energy is going to be equal to 0. So we can take that out of the equation, and we can see that the work done by the non-conservative force is only the change in the kinetic energy. So to find the change in the kinetic energy, we must find the initial and the final kinetic energy. Let's write this here. So the change in the kinetic energy is the final kinetic energy minus the initial kinetic energy. We know that the final kinetic energy will be 0 because the footballer slides to a stop. So therefore at the end his velocity will be 0, and therefore his kinetic energy is going to be 0. Let's calculate his initial kinetic energy. So that is going to be a half times the mass times his initial velocity squared. And so it will be minus a half multiplied by 65 multiplied by 6 squared. And that is going to give us an answer of 1,170 joules. And therefore, we can say that the work done, in this case by the non-conservative force, equals the change in the kinetic energy, which is 1,170 joules. But look at this. this is interesting, we've also derived that the work for the non-conservative force is equal to minus 450 times delta x. In other words, we can now equate these two. Just remember that this is minus, this is a negative answer, the kinetic energy, because the final kinetic energy was 0. If we subtract the initial kinetic energy, we'll have a negative answer for the kinetic energy. So actually, the work done by the non-conservative force is minus 1,170 joules. And physically, that is correct, because the frictional force is going to lead to a loss in energy of the system. The energy is conserved, but this energy will be transformed into friction. The footballer is going to have a roasty on his leg because of the force of the friction on him. Right, so now what we can do is we can equate these two, and we can say that minus 1,170 will equal minus 450 delta x. The minuses cancel out, and by rearranging the formula, we can say that delta x is going to be 1,170 divided by 450. Right, to get rid of the 450, we divide by 450 on the right-hand side, and what you do on the one side, you must do on the other side. And what that gives us is a value of 2,60 meters. And so, altogether, the stopping distance that this player will have will be 2.60 meters. So it's important that we're able to do the calculations like this, taking into account the work done by conservative and by the non-conservative forces. Right. The next topic that we will study is the topic of power. System is work, energy, and power is defined as the rate at which work is done, and power is the work divided by the time. Very importantly, the unit of power is watt. Watt is the unit of power. Now we can show, using information that we have already, that we can write the power in terms of the force acting on an object, which is going to be constant, and the velocity of the object. So let's see how we will do that. Let's write down our equation for power. So power is work divided by time, or the rate at which work is done. Now work, we know, is the force times delta x times cos of theta divided by the time. In this case, let's assume that the force and the distance are in the same direction, and therefore cos of theta will fall away, and we have F delta x over t. Let's rewrite this formula a little bit. Because we're multiplying F and delta x above the line, I can take F out, and I can write this as delta x divided by t. Now the question is, what is the rate of change of distance, or rate of change of displacement? If you remember back, you'll know that this quantity is the velocity. So that means that this part here reduces to the force multiplied by the velocity. And so this gives us two equations for which we can use power, the force times the velocity, and then on the other side, power is equal to the rate at which work is done. Right, and we're going to look at some examples of these calculations next. So first of all, let's consider the following. So what we have is a set of stairs, and the height of the stairs is 10 meters. And we have a student. The student is going to run up the stairs, and the student will run up the stairs in a time of 5 seconds. The student has a mass of 40 kilograms. So the mass of the student is 40 kilograms. What we want to do is want to calculate the power exerted by the student. Right, so we want to work the power, the rate at which work is done. So power is the work divided by the time. Let's write down what we know. We know that the time is 5 seconds. We don't know what the work is. Is there a way that we can calculate the work? Of course, we can calculate the work, remembering that the work is equal to F delta X cos theta. Now, very importantly, what is this force that's acting in this example? You guessed right. The force in this case is equal to the force of gravity, or the weight of the student. And so, remembering that the work must be done parallel to the direction of movement, and only the component of the force that is parallel to the component direction of motion is the one that is going to be acted on. So it's only the height here. This distance is the only distance that is going to be important here. It doesn't matter how long the stairs are, because the force that is going to be overcome is the weight, and that is the force of gravity, which is in the vertical direction. So we can calculate the work in this case, and we can say that the work is then the force, and instead of delta x, we can say delta y, because this is now in the vertical direction, and that equals to the height of the stairs. The force will be her weight. Now, what is her weight? They give us the mass. The mass is 40 kilograms. Now we can calculate the weight, which is the mass times gravitational acceleration, 40 times 9,8, which is going to equal 392 newtons. We can then substitute this value into our equation here, and therefore we can calculate the work. Now remember, the work and the weight are not the same. Don't get confused, because if you use a W for the work, that's why I wrote out weight. Remember, a better way to write the weight is to use the force of gravity, the symbol Fg. So just keep that in mind when doing calculations like this. Right, so we can, knowing that, we can go back to calculate the work done, which is the force times the height. So that's 392, which is the weight, times the height of 10 meters, and therefore this is 3,920 joules. That's the work done. Now to find the power, this is ultimately what we want to calculate. The power is the work divided by the time, which is 3,920 divided by 5, and 3,920 divided by 5 gives us a value of 784 watt. So if you think about this, what would happen if the student ran faster? In other words, the time is smaller. Would the power be greater or less, or the same as when the time is 5 seconds? And these sort of calculations where we deal with concepts is just as important as our calculations. So if you look at this, you'll notice that time is below the line here. The time here is below the line. So if the time goes bigger, the quantity to the right-hand side gets smaller. In other words, the power gets smaller. So by making the time smaller, the power is going to increase. So the faster the student runs up the stairs, the more power will be generated. Right, we're going to look at another example of the power now, and this is quite an important one. It's mentioned in the scope of work that you will receive for the matric, and this is going to be looking at the power of a borehole. We'll now consider a calculation where we are pumping water from a borehole and we want to see the power that is generated by the pump that pumps water from a borehole. So basically the question is as follows. What is the power required to pump water from a borehole of depth 15 meters at a rate of 20 liters per second? So this is a very interesting calculation because there are some things here that you might not know what to do. And one of these things is the rate at which the water is pumped. So if we look at this, we will see, well, we need to work out the power. And so power is going to be the work divided by the time. Work is going to be the force times the distance, which is the height of the borehole. Now what's important to understand here is that the height, we are working in the y direction, we are pumping the water against gravity, and so we can assume that the force and the height are in the same direction, and therefore we don't have to consider the angle. The angle between the force and the direction is 0 degrees, and so we can neglect the cos of the angle there. All right, so what we want to do is we first of all want to see how much water do we bring up. So what is the mass of the water that is moved? So the mass of water is as follows. You should know that 1 kilogram is equal to 1 liter of water. So if the mass of the water that is pumped up is 20 liters, well, the liters are 20 liters in 1 second, it means therefore that 20 kilograms of water is pumped in 1 second. So if we have the mass of the water, that tells us that we can work out the weight of the water, and therefore we can work out the work that is done. Also, when the water comes out, is that the kinetic energy of the water is going to be non-zero. It will be greater than 0. We don't know what the kinetic energy is, but it will be greater than 0. We can also assume that the kinetic energy at the bottom of the well is going to be 0 because it will start from rest. And remember, we are dealing with work and energy, and so we can use this change in kinetic energy to help us calculate this power that's required. Right. So, how do we calculate the velocity at the top? Okay, remember that velocity is the rate of change of distance, or displacement to be exact. So it's the rate of change of displacement. The displacement in this case is the height of the borehole, which is 15 meters. We know that the time is 1 second, and therefore the velocity of the water at the top will be 15,0 meters per second when it reaches the top. So, first of all, we want to work out the work done to raise the water. So the work done to raise the water is going to be work This will be non-conservative work because we are applying a force to the water, working it up against gravity. The water is not just falling down, but the water is actually, there's an applied force on the water to bring it up. So this is a non-conservative work. And that's going to be equal to the change in kinetic energy plus the change in potential energy of the water. Right. And what we can do here is we can say, well, this is going to be the final kinetic energy, in other words, the kinetic energy at the top, minus the initial kinetic energy of the water at the bottom, plus the final potential energy of the water minus the initial potential energy of the water. Right. So, assuming that in the bottom of the well, if that's the well, and at the bottom of the well, the position, the potential energy will be 0 there, because that is given as 0, and the kinetic energy starting off as 0. Then at the top of the well, the kinetic energy is going to be a half mv squared, and the potential energy is going to be mgh. Right. So we've got all the information. We must now substitute it in. We can therefore work out that our kinetic energy is a half mv squared minus 0, our initial kinetic energy is 0, plus mgh minus 0, because our initial potential energy was also equal to 0. Now, if we go and substitute these values in, we'll see that this is equal to a half times, remember the mass of the water is 20 kilograms, multiplied by the velocity of the water when it hits the top is 15 squared, plus the mass, which is 20, times 9,8 times the height of the well, which is 15, and that will give us a final answer of 5,19 times 10 to the 3 joules. We're almost there. So we've got the work. The work done by the non-conservative force is 5.19 times 10 to the 13, 10 to the 3 joules, not 10 to the 13. And therefore, the power is going to be the work divided by the time. So the work is 5.19 times 10 to the 3 divided by the time is 1. And therefore, this is going to be 5.19 times 10 to the 3 watt, because the time that the water takes to move to the top is 1 second. That brings us to the end of this lesson. Thank you very much.